in a presentation on his research on convergence results and a new preconditional for spectral collocation in time. During that presentation, immediately afterwards, the floor is open for questions from everybody. Afterwards, we excuse everybody but the committee and John, and we'll ask a few more, and then the committee will deliberate. John, please go ahead.
Well, thank you everyone for being here. I'm going to talk a little bit about my master's research. Okay, and it's about collocation. So what exactly is spectral collocation? This is an important tool for solving differential equations of any kind. And the key idea is that it provides a systematic construction for approximating solutions of arbitrarily high order. So that's a nice property. And in particular, it's very effective when the solution is known to be smooth. So this is what they call the spectral accuracy. The smoother the solution, the more accurate your approximation. And so here's a couple of examples where people might use spectral collocation. So these orbit problems where you have an ODE that describes some body orbiting something else, whether it's the Earth or the Moon or something like this. Okay, and some more uses of collocation that have become popular recently are for optimal control problems. So in particular, for time discretizations for these optimal control problems. And I've given a few sources here that sort of talk about this. But in particular, one thing that has come up recently are global methods, global collocations for these problems. And that's where you approximate the solution with a polynomial on the entire room. So for example, there's this problem taken from this Mike Ross paper where they simulate the orbit of some body, and you can see that the solution is very, very smooth, and so you can leverage these approximations that are very accurate. Now, what is the current state of these methods? Even though they're very old, some open questions and challenges remain. In particular, in the context of these optimal control problems, convergence for global collocation in particular is rarely presented. So that's one big gap in the literature that we see. Moreover, just on a discretization level, thing that you go to solve, there's really this disconnect with people talking about these methods. So there's a lot of different forms depending on what you choose to do, and there's this equivalence between them, but it's not really ever explicitly stated. And on a numerical note, depending on what problem you go to solve, the sort of dynamics that you encounter may lead to ill-conditioned systems that are challenging to solve. And so, yeah, you would need to do something, for example, say preconditioning to robustly solve these problems. And so this is where my work comes in. So I'll, in this talk, sort of address these three challenges and questions. First, I'm going to go through a convergence analysis for these global collocation methods using old techniques that have, for some reason, been forgotten in the optimal control literature. Then I'm going to sort of make everything concrete, talk about the discretizations, show the different forms, and show how they're all related to each other. And then I'm going to address this numerical issue by introducing a new preconditioner for integration-based collocation methods in particular. So with that, first I'll get into the convergence analysis. Just a bit of literature to review. So these methods are very old. The first work on collocation was done in the late 30s by Fraser and Lanchos. The convergence was really studied by a slew of authors here. By Nico in particular has some results for global collocation for boundary level problems using a bunch of functional analysis tools. And this work was extended in the 70s and 80s by the authors you see here. Since then, though, now that collocation is being used in optimal control, you have very different sorts of convergence analysis. And in particular, this happens for the piecewise setting using a lot of different techniques than you see in the original papers. With that being said, what exactly does collocation look like? So if we consider sort of a very simple initial value problem, y equals some function of y and x, the idea of collocation is to approximate the solution with a polynomial p of degree k. And what do you do to determine what that polynomial is? You select some interpolation nodes in the interval, and you require that the initial condition is satisfied and that the residual of the differential equation goes to 0 at your selected collocation nodes. Okay, and this first inequality here is highlighted in red because there's some extra care that goes into choosing the first collocation point, but I'll get into that in a later section. Okay, so first dealing with the linear problem, we're going to consider a slightly more general setting. Here we're going to assume that A is a function in L infinity and F is in L2, and we're going to consider this linear initial value problem. Right, when the problem data A and F are continuous, this is exactly the same sort of thing that we were considering before, but it's slightly more general in that you can consider functions that are not defined everywhere. A lot in this section, I'm going to assume that these initial conditions are homogeneous just to simplify presentation, but you can go through everything again with non-zero initial conditions. It just makes things slightly more involved. Okay, and with all of these assumptions here, there exists a unique solution to this problem that depends continuously on the problem data, so A or F. Okay, a bit of definitions to begin with. I'm going to define this subspace of functions H1 RC, just H1 functions that satisfy a homogeneous initial condition. I'm going to let D be the differentiation operator that takes a differentiable function and maps it to its derivative. In this context, we'll take functions from H1 IC into L2. And with this definition, the differentiation operator is both continuous and continuously invertible, with its inverse given by this integration operator that you see here. And lastly, I'm going to define this A operator, which just takes a function and returns its multiplication by the A that we see in our differential equation. So with these things defined, we can rewrite the problem that we had in the beginning as follows. So this problem here, where we search for y in H1, satisfying the initial conditions, and also satisfying this equation, can be rewritten like this. And just by defining a new function v to be the derivative of y, we have this equivalent problem here. So these two problems are totally equivalent. The solutions correspond to each other with the relationship you see here. And you see that the solution to the first problem lives in H1, where the second problem lives in L2. And it turns out that this formulation is going to be slightly more favorable to work with in convergence. Right, so why is that? If we define an operator K that takes functions from L2 into L2, just to be this inner term here, we can show that this operator is a compact operator from L2 into L2. But not only that, if A is continuous, like the problems that we care about for collocation, then K is also a compact operator from L2 into C. And you can show this, for example, with the Arzela-Ascoli theorem. Now, the key ingredients before I get into the convergence analysis are going to be these three things. We're going to define some operator that represents interpolation by polynomials. We're going to show that for the right choice of collocation nodes, the right place that we want our differential equation to go to 0, that these interpolation operators converge in some sense. And lastly, we're going to use this compactness property of the K operator. Okay. So let's do those three things. First, we consider a sequence of collocation nodes, so given by this infinite matrix here, that all belong to the interval -1 to 1, and that satisfy this set of inequalities. And to define the interpolation operator, we're going to let these L tildes be the Lagrange polynomials for x1 to xk. And with that, you can define an interpolation operator pk that takes continuous functions into polynomials of degree k minus 1 just by this expression here. Okay, so what are some properties of the interpolation operators? Well, we may know that in general, these interpolation operators don't behave so nicely with respect to the uniform norm. So in particular, this is often called Runge's phenomenon. And basically the idea is that for some functions, you interpolated a set of nodes, but the error in the infinity norm blows up. And it turns out that it's worse than this, and that for any set of nodes, there exists such a troublesome function where you can take as many interpolant nodes as you want, and the function always sort of fails to be approximated well in this uniform sense. However, we can show that there's a different kind of convergence that we have, and in particular, Ergo Chantaran proved that this is the so-called convergence in mean. What is convergence in mean? Well, if you define your nodes in a certain way, which I'll get to in a second, I guess in particular, if you have a wave function which is non-negative on the interval that you care about, and that has a finite integral and a finite integral of its inverse, and if we let these P1 to be in P infinity be a set of orthogonal polynomials with respect to this wave, then we can choose the interpolation nodes to be the distinct real zeros of some polynomial of this form. Okay. So with that choice, under all of these assumptions, then this is the convergence that we get. For any continuous f, we have that sort of this L2 measure of how close the interpolant is to 0, as well as this weighted interval here. So this is a nice property. In particular, this holds for a set of nodes known as the Gauss-Ridal, Gauss-Lobato nodes, which are all related to Gaussian quadrature. So, if we make this choice, if we choose our, get to that in a second. First, going back to what collocation is. So, just as a reminder, the two equations that we consider are sort of this equation with the differentiation operator and an equivalent equation in the derivative of our solution, but with this compact operator k. What do we do to discretize? Well, we require that the residual of these things vanish at a set of collocation nodes. And what that means is that if we apply the interpolation operators to these functions, then this says that they are satisfied at the nodes that you choose. So this is a neat way to represent collocation. And if you look at these equations here, the solution of this guy is a polynomial of degree k. And since this is the derivative, the solution will be of degree 1 less. Now, we're interested if these things actually do have solutions, and if they do have solutions, are those the solutions that we want? Well, sort of applying these ideas that are in this Finito paper, which studies the boundary value problems, we can show the following theorem. So letting these collocation nodes be properly chosen in the sense that we just explained, then for k sufficiently large, so if we choose enough points, these problems do in fact have unique solutions that satisfy the following relationship. And moreover, you get the following error estimates. So here, the norm of the difference, this should be, that's good actually, is bounded by the following term, where ek minus 1 is the error of the best uniform approximation by polynomials. Now, okay, what does this error look like? Well, in order to get sort of a concrete estimate of what your error is, then you need to look at your particular problem. So recall that for the problems that collocation works for, the solution should be very smooth. When your solution is very smooth, then it turns out that this best uniform approximation, the error is very small. And so that's where this spectral accuracy comes from. Okay. Just a little bit of intuition behind how the proof works. We want to show that if you pick k large enough, then the linear operator of the equation that you carried out is continuously invertible. And so how we do this, we use the tools that we just presented. And so, in particular, the mean convergence of Lagrange interpolation implies a couple of important things. First of all, the interpolation operators have uniformly bounded norms, and this follows from the Steinman theorem. And secondly, they converge pointwise to the embedding of continuous functions into L2 functions. So how do we use this? Well, since k is compact from L2 into C, we can show that these interpolation operators applied to k actually converge in norm to k itself, where here k is interpreted as going from L2 into C, and here it's from L2 into L2. We can use this to show the following. Just with some algebraic manipulation, we can rewrite this inverse as follows, and since these operators converge, this term gets very small. This is the solution operator of our original infinite dimensional problem. So this is invertible, and now this is a perturbation of the identity, and so it's also invertible. And so that tells us that these operators are continuously invertible, and they have bounded inverse. And the error estimates that you get come from plugging in the infinite dimensional solution into your collocation equations and rearranging things. So this is the linear case. Now we want to consider the nonlinear case. So here we're going to consider the following equation. This time the functions are continuous. And moreover, we need to assume that the right-hand side function g and its derivative are Lipschitz in their first argument. And with that, there again exists a unique solution that depends continuously on g. And following the same steps as before, we sort of write everything in this operator notation. So we define a function g that just takes a continuous function and evaluates the function g. And with that, our initial value problem can be written as follows. And once again, using this sort of change of variables, you can find an equivalent problem and the derivative of the solution. And again, this problem here is much more convenient to work with in the analysis. It just makes everything work. Okay, so getting into it. If we define this residual operator, which sort of you just rearrange the equation that we saw before, then our collocation discretization can be written as follows. So the infinite dimensional problem is given here. All we do is we define this new operator Rk, which is given here, and we search for a polynomial of degree k minus 1, which we call vk. That satisfies this equation. Okay, the solution to this problem is a polynomial of degree k minus 1, and here it's going to be convenient, since we have this convergence in mean, to consider Rk as an operator from L2 into L2, even though our setting here is continuous functions. Okay, and the idea is that you have this nonlinear problem. How would you go to solve it? Well, you would use something like Newton's method. So in Newton's method, you choose an initial iterative, some function, some polynomial, and you generate this sequence of approximate solutions given by this Newton equation I've written here. So the two questions that you should have at this point are, okay, you have this sequence of approximate solutions. Does the iteration converge to anything as you put out the sequence? And moreover, if a limit does exist, how close is that limit to the real solution, right? So these these are the two questions we need to answer, and we can answer it using the Kantorovich theorem, as you often do for these types of problems. So, the Kantorovich theorem, what you need to show are a few necessary conditions, which in this case are all satisfied, but for details I'll refer you to the thesis. But in particular, we need to show that the derivatives of our collocation operators are Lipschitz with some constant L. We need to show that the initial iterative that we choose is sufficiently close to the true solution. And given these quantities beta and eta, which sort of involve the inverse of the derivative of the collocation operator, we need to show that this quantity is less than 1. Okay. And once we show all these things, a few conclusions are immediate. There exists a local solution to our collocation equation, meaning that there actually is some solution to our collocation problem. And moreover, this solution satisfies this estimate here. So what does this say? This says that the solution to our collocation equation is close to the projection of our infinite dimensional solution with this distance here. So now, sort of, if you look at this, this is kind of similar to what we had before. This is a measure of how well you can approximate your infinite dimensional solution by polynomials. This time, we're measuring it in L2. So you can get estimates for what this error looks like by considering, a given set of collocation nodes. And the last thing that we have is that Newton's method, given by the iteration before, converges quadratically to the solution of the collocation problem. Okay, that's our convergence analysis. So now that we know that these methods can work, what do they actually look like? So that's what I'll get into next. Okay. Going back to this linear initial value problem, this time where all of the functions are continuous, we consider the problem that you see at the top. Now this might seem like sort of a restrictive problem, but it's really not. You don't lose that much generality. For one, because more general domains transplant to -1 to 1 just by a simple change of variables. And secondly, when you go to discretize the nonlinear problems and you solve the resulting system of nonlinear equations with something like Newton's method, at every step you solve a Newton's equation for which the linearizations look like discretizations of the linear problem. So by considering this problem here, we basically know what it is that we'll have to solve in any case. Okay. With that being said, recall the idea of these methods is that we approximate the solution of our equation of polynomial, we select some interpolation nodes, and we require the initial condition is satisfied and the residual goes to 0 at some of the nodes. That's the idea, but to get an actual concrete discretization, what we need to do is choose a polynomial basis for P. So there are many choices. The most typical one that you sort of see in the literature is the Lagrange basis. And so you can represent P in the Lagrange basis polynomials L0 to Lk as follows. And if you recall just from the definition of the Lagrange basis, when you do this, you require that all of the nodes are distinct, meaning that the first collocation node has to be different than -1 in this case. Now, the Kronecker properties of the Lagrange polynomials imply that the coefficients in this expansion actually are the values of the polynomial at the points, and therefore the coefficients are our approximate solutions, sort of evaluated at these discrete points. And just sort of inserting this expansion into the collocation equations that we had before, this is sort of our first pass at what a concrete discretization looks like. It's not very good to look at, so what we do then is we prescribe a data layout. So in particular, we accumulate these Lagrange polynomial derivatives evaluated at the collocation points into this matrix D. This is sometimes referred to as a subblock of the spectral differentiation matrix. And we arrange our data, which are the coefficients of our polynomial basis, into a matrix whose columns correspond to collocation nodes. And similarly, we define this matrix F to be the right-hand side evaluated at the collocation nodes. Finally, we define a linear operator A, which acts on matrices of this size. And what A does is it applies the function A evaluated at the jth collocation node, and it applies it to the jth column of its input. Okay. With these quantities in mind, we can then write our collocation discretization in this nicer form that you see here. So this becomes this. I should mention at this point that this is a little bit non-standard. So sometimes in the literature you'll see either your data arranged in one long column with some Kronecker products, or you might see the transpose of this where the data is just arranged row-wise instead of column-wise. But this is how I choose to do it. Okay, so what's the problem with this? Well, it's long been noted that these discretizations suffer from poor conditioning. The differentiation matrix D is known to scale, is known to have a condition number that scales like k squared, regardless of what points you choose. And therefore, people have tried to develop more robust methods by preconditioning these systems based on approximations of D. In particular, you find some low-order finite elements or finite difference preconditioners, or these so-called integration-based preconditioners here. You'll notice though, if you precondition with an approximation of D, or its inverse is what you end up using, then the perfect such preconditioner is the exact inverse of D. And this is noted by Wang, and he says in this paper that the preconditioning that you do is equivalent to what he calls an integral reformulation. That is, changing your differential equation to an integral equation and then discretizing that. And I'm going to show you exactly how that works and how it relates to the setup that we presented. So we at first chose to represent our polynomial on Lagrange basis, but we can also represent it in other bases. For example, this so-called Birkhoff basis. This basis is given by a different set of Lagrange polynomials. So now these tilde L's are the Lagrange basis for the points x1 to xk, and we have a first basis function of 1, and then the rest are these integrals of the Lagrange basis. Since the Lagrange basis for the nodes 1 to k, since that's how we've defined it, now we can actually allow that the first collocation node is equal to the initial node. And this is important for some methods that you may have seen, Lobato methods, Dow methods. But then we sort of go through the same steps. We write our polynomial in this expansion, we insert it into the differential equation. And one thing that falls out just from the Kronecker property of these polynomials is that what do these new coefficients actually mean? Well, the first one represents the value of the solution at the initial point, while the rest of them represent the value of the derivative of the solution. Okay. Like I said, we do the same thing as before. We arrange our data into matrices where columns correspond to collocation nodes. We define this matrix B, which is just our basis polynomials evaluated at the collocation points. And I'll note that this matrix is actually referred to as the spectral integration matrix a lot, just because of the way it acts on vectors. I'll talk about this a little later. But with these things defined, we can define two new integration-based collocation discretizations. One whose variables are the derivatives of our solution, and then using this change of basis, which is just evaluating our Birkhoff polynomials, we get this totally equivalent y-based or B-based formulation in the values of the solution itself. Okay. Now, how are these things all related? Well, first of all, the three formulations that I just presented are totally algebraically equivalent, meaning that the solutions correspond to each other and you have some sort of isomorphism between them. However, if the nodes are distinct, meaning if all of them are separate, and you can actually write down these D-based discretizations, then you can show that D is the exact inverse of B, and the B-based formulation in the Y variables is obtained from left preconditioning the D-based formulation. And this is exactly what Lang was talking about in this paper, how preconditioning in the perfect sense is equivalent to an integral reformulation. Furthermore, if you take a look at the two B-based discretizations, it's known that these are actually equivalent to Runge-Kutta steps. And in particular, the Butcher tableau that you get, the A matrix that you normally see in Runge-Kutta methods is given by the spectral integration matrix. And the C and B that you would normally have in the Runge-Kutta method are given here. Moreover, I've shown that the linear operators of these equations, so the left-hand side of the red and blue equation, actually have the same spectrum, so for the same eigenvalues. And so when you go to solve something like this, for example, using an iterative method, you might expect that the iteration takes sort of a similar path, although not the same, because these linear operators can have different eigenvectors. Okay, just as a quick example, taken from this one paper, we have a linear initial value problem, and we discretize using the three discretizations that I just presented. The solution is smooth and it's oscillatory, it looks like this. And you'll notice that the D-based formulation, if you take the condition number of the resulting matrix that you need to solve, the D-based formulation has a condition number that grows, while the two B-based formulations remain constant. And so this is why people sort of like these B-based discretizations. Now, in order to solve these B-based formulations effectively, we need to consider a few things. In particular, we normally will solve these using an iterative method, for example, like GMRS. How much does this cost? Well, in general, you can't say that it costs less than order k cubed operations, which is about like a direct solve, because the total number of iterations that the outer loop takes is the size of the system, which is k times ny. And at each inner iteration, you need to apply the left-hand side. So you apply k by k matrix, this is k squared, and so in total you get these k cubed operations. Now, for a lot of problems, even though these B-based discretizations can be more well-conditioned, the complex nature of the solution of these problems can ruin the conditioning of these discretizations. Curiously though, no one's really considered preconditioning these B-based discretizations, even though there's all these methods to precondition the D-based. And so this is where I come in. So first, I'm going to go through how we can sort of reduce the cost of these two things. Now, I'm going to consider the second discretization using the Y variables, and I'm going to define this Z operator just to represent the left-hand side of this discretization. So remember from the convergence section that we need to choose the collocation nodes in some smart way, corresponding to the nodes of some Gaussian quadrature. And here I'm going to choose the nodes associated with Chebyshev Gauss quadrature. So these are given here, they have a closed form solution. And the reason that people tend to do collocation at Chebyshev nodes is that there's this nice relationship with a discrete cosine transform with which you can reduce the application of the left-hand side to just order k log k operations. So how does this work? Well, it all stems from the fact that the spectral integration matrix has this name because you can think about its application to a vector as doing the following three things. So the application to B, the application of B to a vector V in Rk, first interpolates the values of V at the collocation nodes, integrates that interpolant, and then evaluates this primitive back at those same nodes. So if you just take that, then B itself can be written as the composition of three operators, where V maps coefficients in a Chebyshev series to values of that interpolant at the collocation nodes, and S is some matrix that performs integration in a modal sense or integration on the coefficients of a Chebyshev series. It turns out that this integration matrix in the modal sense corresponds to a sparse matrix, and so it can be applied quickly. And these V maps, which map values to coefficients and vice versa, are nearly identical to a discrete cosine transform. And it's well known that this can be implemented in an effective way that you can apply these transforming k log k operations. And given that, you can apply the operator Z for the left-hand side of these discretizations in k log k operations. Okay, so that sort of takes care of the cost of applying the left-hand side, but now we go back to these iterative methods. So in general, the convergence of an iterative method is related to the spectrum of the linear operator. In general, we want the eigenvalues of the linear operator to be clustered, and if the linear operator is sort of close to normal, then the iterative methods converge quickly. So in practice, what people do is they try to accelerate convergence by solving an equivalent problem. So they introduce this preconditioner Z tilde, and now they solve this instance of right preconditioning, as is known, where you insert the preconditioner here, and now you solve for a new variable which is related to the solution you want through this equation here. So this is what we do, but for us, we define this preconditioner to be exactly the form of the original linear operator, just with the spectral integration matrix replaced by some approximation. And this approximation comes from quadrature. Exactly what that is, okay, let's go back to what the integration matrix is. We let V be some vector, and P interpolate its values at the collocation nodes. Now, since the ith component of V sort of interpolates this function exactly until the ith node, you can write the ith component of this product as follows. So this integral here, which you can rewrite as an integral over the entire interval using the Heaviside function, which I've defined here. This is just a step function with the value of 1/2 at the discontinuity. So the idea now is to approximate this integral using quadrature. So we want quadrature at the nodes that we care about, except now we want quadrature with respect to the constant weight function omega equals 1, not the Chebyshev weight function with which these nodes are associated. So we let omega tilde be these quadrature weights with respect to the constant wave function, and in the literature this is known as the Fayer weights. So then what we do is we approximate.
Can I ask you? I'm lost just a bit. This seems to me that the ith component of EV is that because it interpolates up to the ith node. Can you remind me why is that? Why does it interpolate up to the xi node?
Because B just sort of I may not have written this in the slides very clearly, but what B does is B is a matrix of the Birkhoff polynomials. The ith row of the matrix is the polynomials evaluated at the ith node. And so what you're doing is you're evaluating some polynomial expansion at the ith node that you care about. And since these polynomials are of the right degree, if you apply this to a vector of polynomial coefficients, then this all works. It's exact.
It's specifically because you're doing the ith row at the ith point. It's not because of anything before, like that you're integrating from -1 through all the way up to xi. It's because of. I think I follow. So
Okay.
thank you.
Maybe you can ask me after.
Maybe.
If it's still there.
Yeah, so the Bij is equal to the integral from -1 to xi of the ljth, of the jth Lagrange polynomial. So the row I determines the upper limit of integration.
Yeah, okay, got it.
Thank you. Okay, just with this definition, the quadrature approximation that you get, so the B that we use, looks like this. So it's a lower triangular matrix with constant columns below the diagonal, and the columns correspond to the quadrature weights. So this is what it looks like. This is the real integration matrix, and this is the approximation. You can see just in the eyeball norm that this is a pretty good approximation. And in fact, we've shown, so me along with some collaborators at Sandia, that as k tends to infinity, this quadrature approximation does converge to the true thing in the infinity matrix norm at this rate. And from this, it follows that the eigenvalues of our preconditioned system, whether it be left or right preconditioning, the eigenvalues all converge to 1 as k tends to infinity. And this is exactly what you want. This is what these are as well clustered as your eigenvalues can be. The last thing that we need is that, we have a good preconditioner that clusters the eigenvalues, but is that preconditioner efficient to apply? And just from the definition of what the approximation is, it actually turns out that its application is this cumulative sum. So you can apply it in order k operations, and if you have that A can be cheaply inverted, then the whole preconditioner can be inverted very cheaply. And so when does this happen? So if, for example, the dimension of your solution is much smaller than the number of collocation nodes, which is exactly sort of the scenario that we care about in these higher order global collocation methods, then this preconditioner is very cheap to apply and invert. So we can expect to have good order k log k iterative solves if this Z is a good approximation, which I just showed. So we can expect good solves. So let's put this into action. The first example I'll talk about is this linear initial value problem, taken from this paper here. This is sort of an example that gets passed around a lot. It has a closed form solution, which is written here, and this solution can be approximated essentially to machine precision by a higher order polynomial. First of all, if we apply our 3 collocation discretizations again, and we solve using an iterative method just to see what happens, without any preconditioning, what happens? Okay. Well, the D-based formulation, you can see the convergence is extremely slow. In fact, it takes the full amount of iterations to finally converge to the solution. Whereas these 2 B-based formulations perform similarly, right? And they take much fewer iterations, and they all return essentially the same solution. It's just the cost of getting to that changes. Now, if we focus on this yellow discretization, which we now have this nice preconditioner for, and we look at how this scales as we increase the number of collocation points, we can compare 3 things. First, we can compare sort of everything that we've just explained using a matrix-free discrete cosine transform-based method with preconditioning. These solves scale as you increase the number of collocation points. The runtime scales essentially like order k, which is really nice because this enables solves of up to and over 1 million collocation nodes, which is extremely good. If you instead use the same iterative method without the discrete cosine transform, then your inner loop requires these order k squared operations. Now the runtime of your method is k squared. Since you precondition, you still have somewhat fast solves compared to a direct method, which is in yellow, and takes order k cubed. The second example I'll talk about is more of a practical example. This is a nonlinear problem. It describes the orbit of a body around 3 other bodies, and with the right choice of initial conditions and parameters, this produces a periodic orbit with the period you see here. Recall that these nonlinear discretizations, you need to use Newton's method. And so how does that look? Well, discretizing with collocation gives you a system of nonlinear algebraic equations that look like this, where sort of like the A that we had before, this G operator applies the right-hand side of the differential equation in a column-wise sense. So again, when you solve this with Newton methods, the linearizations that you end up solving look like these linear discretizations. So we solve this problem with an exact Newton method using a backtracking line search. And what are the results? In red, you see this MATLAB ODE78, which is sort of just a high order adaptive Rubik-Kutta method. And in blue, we have our collocation method, which is initialized to the red curve. So if we look at the iterations required for the discretization unpreconditioned versus preconditioned, we see that the Newton iterations are similar. But the average number of GM-res iterations significantly drops. And you see that by the time you hit, say, 4,000 collocation nodes, your preconditioner is already very, very good in the sense that you only need 2 GM-res iterations to converge to the solution. One thing that you might be curious about is, okay, we have this sense of preconditioning works well if your matrix is close to normal. How close to normal is this system? Well, I here just plotted A transpose A minus A transpose, the norm of this, where A is the system matrix that you need to solve. And it's actually quite large. I mean, this is a big system, but here the sort of the amount this deviates from being a normal matrix is substantial. And even in spite of that, this preconditioner seems to work very well in this case. Okay, just to sort of wrap up, what have we done? What have I done in this talk? I have presented a convergence analysis for these global collocation methods. I've demonstrated that the collocation discretizations that you see in the literature are all sort of equivalent, and you can represent all of them by choosing the right polynomial basis. I've introduced a new preconditioner for a certain type of B-based collocation discretization that enables very fast solves that scale to over 1 million collocation nodes. Now, in the future, there are a few things that I think would be interesting to do. For one, we showed that the 2 B-based formulations have the same spectrum, but we saw that the GM-res iteration history isn't exactly the same. So it'd be interesting just to sort of explore that further, see if one is better in certain settings. Furthermore, this preconditioner sort of has a natural application of finding periodic orbits. So when you don't know what the period of your solution is, you can sort of find this by setting periodicity as a constraint and then sort of extending the preconditioner using something like Schur complements. And finally, I think it'd be really cool to sort of take these tools that we have in the ODE setting for the convergence analysis and apply that to the optimal control setting, where these techniques have long been forgotten, and see if that simplifies the convergence results that you see there. Okay, with that, I'd like to thank my collaborators at Sandia and open the floor for questions.
Moving on, are there any questions from the audience? Seems not to be the case.
Wow.
Right, I mean, okay, so we yeah, I know your question. Well, then, if there are no questions from the general audience, we'll ask you to leave